So a few weeks in now, we're in week 6, 7, right? Week 7 of programming, right? Our programming careers. It's a good place to take a step back and talk about big O notation, right? Big O notation is a way to calculate or to measure the performance of your algorithm, right? So you have a function, that function takes in some input, you have some logic in that function. What is the performance of that particular function? How much work does it take that function to do, given a certain input? Given input n, where n is the number of elements or whatever it is, what is the performance of that algorithm, right? Let's take a step back. For example, if I was to give out a message, right? I have a message to give. Is it more efficient for me to give the message to each individual in an individual room? Is it more efficient? Or is it more efficient for me to come up here and give out a message to everybody? What's more efficient? The second one, right? Where I'm giving that message to the entire audience, correct? Right? So here, that's like a typical case of big O notation. How much work is my function doing? How much work is the logic in my function doing to execute that particular algorithm, right? That's what I'm talking about. Am I going through each individual to give them a message, or am I standing up here and give out a message to the entire class, right? One is more efficient than the other. That's exactly what big O notation is. What is the performance of your algorithm, right? In our lesson here, big O notation captures two types of efficiency. The most common efficiency we talk about in big O notation is time complexity, the runtime. You'll see time complexity or you'll see runtime being used interchangeably there. But time complexity is the most frequently asked. So when you go to a Google or Facebook or whatever company you go into, right? Foursquare, Yelp, whatever company you go into, most likely it will be asked at the end, what is the runtime of your algorithm? Or what is the time complexity? But also keep in mind, there's also space complexity. How much memory is your algorithm taking, right? If you have an algorithm, are you creating 3 additional arrays to store information? Each additional array you create takes memory. So the less arrays you create, the less memory, the more space efficient that algorithm is. So there's 2 things. What is the runtime, time complexity, and what is the space complexity of that algorithm? How much memory? So space, again, is interchangeable with memory. How much memory is that algorithm taking up? Are you taking up extra memory with that algorithm, right? We'll talk about algorithms in place and sorting in place and all that stuff later. But for now, those are the 2 efficient parts of the big O notation. One, you have time complexity, which is the 80% of the time, that's what you'll be asked over space complexity, right? So the minute you execute your algorithm, know the runtime of it. Yes, go ahead.
I'm sorry, maybe you said it and I missed it. What exactly is DSA?
So DSA, in here, we're saying DSA is data structures and algorithms, right? Most people just spell it out, the whole thing, data structures and algorithms, but basically DSA is data structures and algorithms, right? So sorry there, but that's what it means, right? We probably spoke about it earlier in orientation as well, but when you see DSA, that's what it means. Data structures, an array, right? Algorithms, you have some sort of sorting algorithm. So those are the 2 differences. Cool? Great. So this is big O. Let's practice what big O, how we could determine what the big O or the runtime of an algorithm is. So let's go to Playgrounds. Open up a Playgrounds. And you could call it big O notation. And I'll also slack out this chart here. Can we all see that chart in the back? Can we all see that chart in the back? Right? So this is a big O chart. It basically graphs out the different runtimes on an algorithm. So as we see, the very bottom Can we see the very bottom here where it has big O of 1? The bottom right of the chart. Do we see that? Let me slack it out so we all have it. Did we all get access to the big O sheet? Did we all get access to the link I sent? Lilia, you have it? Does everybody have that chart? Make sure you bookmark that chart. Make sure you bookmark it. Okay? So, if we look at our chart, on the y-axis we have operations, right? Do we see operations? And on the x we have elements, right? So that's the chart here, that's the big O chart. The most efficient algorithm, it is big O of 1. Do we see big O of 1 here, where I highlighted it at the bottom right? We see big O of 1. Big O is a big O, like capital O, right? So big O, it's read as big O notation. Big O is a capital O here. Parens, in the parens is the runtime. In the parens is the runtime. In that case here, we have big O of 1 in parentheses. That's constant time. Big O of 1 is the most efficient runtime you could have. Big O of 1 basically says, go ahead and pick a random fellow from this class. I go ahead, I pick Matt. That's constant. If I have to go through each person's bag and see who took my muffin, right? That here, I need to go through each element or each fellow. If I have to go through each fellow, that becomes linear. I have to go through each fellow, right? We'll talk about linear time. But for now, know the most efficient runtime is big O of n. It's constant. You have your array, you access element 5. That's a constant runtime, okay? Next up, we have big O log of n, right? I will also slack out a description of what logarithm is. Back in math class, we did logs, right? But for now, second up after big O of 1 or constant time is log n, right? Log n, we'll talk about binary search, but log n basically takes a problem, like it takes this class, all the fellows here, it splits up in half, then it splits up in half until it gets to that solution. That's log of n. Every time you go through the problem, you break it up in half. So that's binary search. We'll talk about binary search later. Then we have big O of n here. You see, so as we go up, the runtimes get slower. Everybody? Right? So the bottom here is the faster runtimes. And as we go up to this really bad area here, you see that red zone here? Right? As we start going up to big O of factorial, that's like really bad runtimes, right? So you want to stay in the green and yellow here. So big O of n, as I said, is linear runtime. I need to go through each fellow and give them a message. So that's linearly. I go through some array and I print each element of the array. That is linear. We've all used dot sorted, right, from Apple's document. Go ahead.
What did you call those again?
Those are slower runtimes.
I know what you call them.
No, they're not all factorial. Wait. The last one you see here with the n exclamation mark, that's factorial, right? That's the worst runtime on that particular chart, right? Okay, so let's go back to talk about n log n. So we said log n, it splits the problem in half. Everybody? With our sorted closure, when we try to sort an array, Apple's sorting algorithm is n log n, right? The sorting algorithm they're using, we'll do sorting algorithms later in unit 3 and 4. The sorting algorithm here is n log n. You're using a sorting algorithm, is n log n. First, it needs to go through the elements and then break the elements in half until it sorts them correctly. So that here is n log n. Next, we have big O here. big O, n squared. Big O, n squared. That means I have a for loop. I'm going through fellows, a fellows array. So I'm saying for fellow in fellows. Inside that for loop, I have a next for loop. And I'm saying for fellow again in fellows. So I'm going through the same collection twice, right? The first array, and I have an inner array. I have an inner array going through the same collection. Be very careful there. The same collection. If I have fellows in the outside array, in my inside array, I have a different collection. That's not n squared anymore. That's n times m, okay? We have the variables, n meaning n number of elements. If you have a different set of elements, you could have a different variable, call it m, okay? So I'll stop here and then we'll look at playgrounds and see what those runtimes look like and how to derive. The point of the exercise is to derive the runtimes. You see an algorithm, what is the runtime of that algorithm? Okay, let's go to playgrounds. And again, you could call your playgrounds big O notation and keep that playground somewhere, right? Keep it somewhere. What have you guys been doing? Have you been pushing like playgrounds to your GitHub? Any reason why?
Oh, I just keep it on the file. Just push up the meeting files.
Like when we do something in class like this, do you keep it local or you push it? You keep it local? Okay. Everything we do, try to keep it on GitHub. For the example that we're doing right now, let me show you guys something. Go to your browser. Go to your browser and type in gist. So the same way I have it here, we all know our GitHub usernames, correct? Yes? Do we all see the URL I have in there? It's gist.github.com/my name. Let's all go to that URL. What? Oh, your name, your username. So gist.github.com/Chelsea, right? Whatever your username is there. Are we all on a gist page? I'll go to my gist page here. That's fine. We'll create one. So to create a gist, do we see your profile image on the right side here with a plus sign? Everybody, click on the plus symbol. Right where my image is, let me zoom in here. Do you see the plus symbol? Click on the plus symbol. So that's attached to GitHub. You have a GitHub account, you have a gist as well. So the gist allows you to create small code snippets or whatever it is. It could be any extension. Well, compatible extension that GitHub understands, right? So it could be .txt, it could be .swift, it could be .c, it could be .cpp, it could be whatever. As long as it understands the extension, everybody? So click on the plus symbol here. If you click on the plus symbol, we all got a new canvas, right? Like a new editor. So a couple things we could do. The description of the gist, whatever the gist is. So today we're talking about big O. I could say big O notation here. For the file extension, I could put in big O notation. Here, I decide on the extension I want. If you want to have a Swift extension, you say .swift. If you want to have a Markdown extension, you say MD, right? If it's Markdown, you could say MD for Markdown. If it's Swift, you say Swift, right? Whatever extension that you want to edit. Everybody with me? All right. At that point, I could simply do. You could put comments here as well. But whatever file we finish with today, any file we finish with today, you could paste it in here. Everybody with me? When we finish with our playgrounds file, you could paste it in here. Everybody understand so far? Yeah. Well, the playgrounds file already is .swift. But I'm saying the contents of it. You copy it and you paste it into your gist. Or you create a new gist, whatever you want. But get in the habit of creating small gists. That way you could go back to it very simply. It could be something very simple. Like, how do I do X in Swift? You create a Swift a gist on GitHub. You could make it public or private. That way you could access it very quickly on the web. Cool? All right, so here I could write Swift code. Well, I could write like a simple Swift code in here. I need to render. So for I in 0 to 10, pretty soon GitHub is gonna be Xcoding itself, right? I could say print I. So remember, it's a Swift file, so if I save it, the syntax will also be changed. So let me zoom back out here. Those are the two options. So let's focus in. I could create a private gist. Create secret gist is making it private. Okay? Creating a secret gist makes it private. Or I could create a public gist anybody could see. Everybody? So here I just create a public gist. And that's my file. There's my file. Right, so here's my file here. So at the end of the lesson, just paste in whatever we finished with in your gist file. Cool? So it's on your GitHub. Great, yes?
So you have to add file.
Let me go back. Add file, where am I? Before I submit it, so let me create a new one. It's just the next file at the bottom. It just creates you a new file, so you could have multiple files in that. Yeah. It doesn't take you, yeah. Very good. All right, cool. So at this point, we know what a gist is, right? I could create a public gist or a private gist. It's part of my GitHub account. Good? All right. Cool. Let's go back to Big O. So we'll stop on talking about Big O n squared here, and we'll go back to playgrounds as we were before. Okay, so let's first say what Big O is. So here we said Big O notation, calculating the performance of a given algorithm Big O has two performance metrics. We have time complexity, and we have space complexity. All right. And according to our chart, I will list slowest to or fastest to slowest runtimes. So fastest to slowest runtimes. And in runtimes here, as I said, analogous with time complexity. So fastest to slowest runtimes. We have big O of n, constant here, constant time. Right? Constant time, you pick a random element in your array. So I say array subscript 10, that's constant. Get me the element at index 10. Everybody with me? Okay. We'll see some examples of the most common ones. So this is big O of 1, or constant. Then we have big O log n. Right? Then we have big O of n, which is linear time. I'm sorry? Log of n, whatever the n is in the, like say you have log 16, it will take 4 cycles to run. All right, so big O of n here And next up, we have n log n. Next up, we have n squared. To get to the caret symbol is right above your 6. So if you do shift 6, you'll get the caret symbol. The caret symbol is this symbol right here. Everybody? All right? All right, so that's n squared. Then we have big O to n here. We won't get into those today because we haven't spoken about recursion. But when we talk about recursion, we'll see how Fibonacci is 2 to the n. And lastly, we have big O factorial. And factorial is the exclamation mark here. So what I'm saying here is big O n factorial. How many permutations is in an element? For example, 4 factorial is 24. We'll get into factorial later when we talk about recursion. Great. So those are the fastest to the slowest runtimes. Let's see some examples. So when we talk about big O or constant time here, big O of 1 or constant time. If we were given a function print first element. I was given a function print first element. I'm passing in an array, a string array. I'm saying guard, get me the first element. I'm using the guard to get me the first element on that array. If I do have elements in the array, I say print first. Right? So that's constant time. Why is it constant time? Because I come in here, I have an array, right? Keep in mind, I'm not going through every element of the array, right? I am not going through every element of the array. You have to focus on what the function is doing, right? Not the input. The input is an array. I have an input, it's an array. But what is happening inside here, right? Inside here, we have a guard statement. The guard statement is saying array.first. Array.first is always that first element. Everybody with me? It doesn't go through the entire array. It's very similar to saying array, open square bracket, 0. So here, this is a constant time algorithm, right? Get me the first element in the array. If it exists, I unwrapped it using a guard. If it exists, print the first element. So you were given an interview question. They told you to use a function to print the first element in an array, right? First off, if we do this, let me comment that out. If I say print array at 0, is that good code? Anybody? Is that code that you should submit for a code review? Like say you're getting a job or you're applying to a job, right? Why? Everybody heard Tiffany? So Tiffany's saying, if there's no elements in my array, accessing element at 0 will crash my app. Everybody agree? Lilia, do you agree with that? Yes.
So why would it not crash if it has first?
Because first, what does first return us? But what type? Or what data type? Is it just a string or optional, right? That's why we love optionals. Here we have an optional. Thank you very much, Chelsea. So here Chelsea is questioning like, why doesn't it crash with our guard statement? Because our guard statement is protecting it. It's saying, unwrap this. If there is a value, give it to me. And in that case, if I have a value, I print first here. Right, everybody? So don't rush to, you have a code challenge or you're sharing your screen with an interviewer, and they're like, hey, get me the first element in an array. Please don't rush to this. Don't do that. right? Use a guard, use an iflet, whatever you're doing. Don't assume that array has elements in it.
But I could guard array index 0. I could do that, and it would present it.
No.
No.
You mean like guard and then you index in 0? It will still crash, yeah.
It would still crash.
Because you're doing the indexing first before the guard. You're doing that inner calculation first before the guard sees it.
Oh,
You see what I'm saying?
yeah.
So it's still gonna crash the app. So the best way to do it is making sure that there is. You could also say is empty, like guard against is empty. You could do that. But in our case, we're saying if there's a first element, just get me the first element, and I could just print the first element. Okay, so that's a little backtrack here from talking about big O, but it's good because we know what guard is really good for. And guards are great for this particular instance here. We want to print the first element, we guard it, and we print the first element here. So let's test out that particular code. So print first element. It's a string. So here we pass in Greg, we pass in Matt. Right? We pass in Greg, we pass in Matt. I run my application. And I get Greg, right? So again, that's constant time. Everybody? That is a constant time operation. We're looking at the entire function. We're looking at the entire algorithm. This here is the entire algorithm of the function. From line 15 to line 18, I need to evaluate everything that's happening in order for me to tell my interviewer, yes, the runtime here is constant time. I cannot jump to conclusions. I can say, oh, because I see an array here, oh, it's linear. I cannot do that. That's not the way to do it. To derive runtimes, you have to see what the function is doing. Go inside the function's body and see each line what's happening. Never jump to conclusions with that, right? It's very easy to get lost there or jump to the wrong conclusion. You want to see every line, what every line is doing. My first line, is it iterating through anything? No. What is my array that's first doing? It's getting the first element. That first will always be the first element. Doesn't matter if it's a million objects. Everybody with me? Even if it's a million objects, it will always be constant time because it gets the first element. Get me the first person in line, right? It doesn't tell me search everybody who has a red shirt. That would be linear, right? But get me the first person in line. That's constant. Any questions?
Are we determining the runtime ourselves? Does this mean we're going to know how to calculate?
Yes, like based on what we did right now. So you write this algorithm, right? The interviewer at the end would say, hey, Greg, what's the runtime of this algorithm?
And just based off the context of what we're trying to read.
Based on the context we have here on the screen,
It's going to give us that information.
you will deduce, you will give them that information. Yeah, not the playground, but you. Yeah, cool? Good.
When I was going through it, so like the O stuff, you don't have to know like the actual.
The O means big O. The O signifies big O. That's what it stands for.
But like what I'm saying is like in the computers, it was saying that like different computers had different times. So we're using.
We're not looking at the time, like the seconds the algorithm runs. We're not looking at the seconds. We're looking at how much work it is doing, right? I don't care like how long it takes me to give the talk here to the whole classroom, right? What I care is it's more efficient to give the whole classroom the talk than to go through each individual, right? I might go through each individual and take 10 seconds, right? And stand up here and take an hour. But to me, it's more efficient. To the world, to everybody, it's more efficient if I stand and give the entire room that. Exactly. Very good. Very, very good. Cool. Any other questions? Okay, so if I have, where's my array? I don't have an array. Let me create an array. Let me create a let fellows equal to Mel Julia Stephanie Okay. On line 23, what is the runtime of fellows subscript 2? What is the runtime of line 23? Why is it a constant? Everybody heard a mini, right? What time did you come up with, Jahid? Very good. So it's not iterating through the whole fellows array. Everybody with me? It doesn't iterate through the whole fellows array. Great. So here, still constant time. Great. So for fellow in fellows, print fellow, sorry. Print fellow. Great, so we answered that. Anna, what is the runtime of this algorithm, 29 through 31? Good, that's a start. So Anna says it's not constant, we agreed. Walk us through it, what is it doing? If it's going through each fellow, what runtime is it? So let's go ahead, Matt.
I think so.
Why?
Because n is like the amount of times.
An n here is, in that case, we have 3, right? So Anna, Matt was helping, he says it goes through the fellows n times because n represents the amount of elements, right? So here, we could put some notes here. So n, when we say big O of n represents the number of elements in the collection. I say collection because we could have a string, we could have whatever it is. So n represents the number of elements in the collection. So here we have, how many elements do we have in fellows? 3. So how many times we expect the print statement to happen? 3 times, very good. So that's n. So n here is 3. So the big O of that particular algorithm is n times, where n represents the number of elements in that array. Cool? So if we were to run it now, look at that. You see what Playground gave us? Playground gave us 3 here. Do we see the 3, everybody? Everybody? As opposed to earlier, we got nothing. Greg just printed. It just printed Greg. There was no x times. It just happened. With our fellows, we have 3 now. So if we have 1,000,000 fellows, it will go through it 1,000,000 times. That's the amount of work it needs to do to print. Everybody? Again, we're not talking about the seconds or nanoseconds. We're talking about the work it's doing. How much work is it taking me to go through each fellow and give them that message? If I have 30 fellows, I have to go through 30 fellows. If I have 50 fellows, I have to go through 50 fellows. So that's why we're like, yes, go ahead.
I'm not understanding the end times.
Okay, that's fine. That's fine. Yeah. Question in the back?
No. I was just saying that time is like confusing in this sense.
Time.
Yeah, because you're not dealing with actual time.
Yeah, we're not talking about time, right? In here, we're talking about the runtime as it took three iterations to finish that print statement, to finish iterating through the fellows. It took 3 cycles. All right, very good. So back with you, Greg. So n here represents the amount of elements in the array, right? So when I say big O of n, it will take me big O of 3.
Okay.
So if you substitute,
N can represent any number.
Exactly.
It could be like 1 or 2, but as long as they're.
The amount of elements in that array.
Okay.
In our case here, you substitute n with the number of fellows, it's 3.
Okay.
Right? Does that make sense?
Yeah.
Where 1 is just instant. Does that make sense? So if I was to say, what is the runtime of this, and I put in big O of n, I could simply substitute this and say big O of 3, for example. Does that make sense?
Yeah.
Where 3 is the amount of elements in that array. Right? And as that grows, I need to go through more fellows.
And then what is O1?
So O of 1 is constant, right? Like imagine you don't have 3 here and you have 1. So you're only going through it once.
Oh, okay.
Does that make sense?
Yeah.
So that goes back to this guy. Only goes through it once. There's no iteration, there's no loop. Cool? Very good. Very, very good.
So to answer your question, you could say runtime of 3.
No, n. No, not 3. No. N is fine. The interviewer at that point, they should know what that means. Cool? Yeah, so n or linear, right? So here we say 1 second, 1 second. Let us just put some, since we need to keep those notes really handy, let's make it look visually catching right away. So I'll just use some lines here to separate this. And here we started talking about, we kind of jumped here a little bit, but that's fine. Here we're looking at big O of n. Yes, question in the back?
Yeah, so only for the big O, there's only like 3 options. X amount of
It doesn't matter if somebody was to tell you, go find a fellow with a red hoodie, right? Right?
I understand that's a constant, but like.
Well, that's not a constant. If I was to tell you, go find me a fellow with a constant hoodie, with a red hoodie, you'd have to go through each fellow, right? You'd have to go through each fellow. So even if the third fellow is the one in the red hoodie, the worst case, we'll talk about worst case, you're always looking at the worst case scenario. Worst case, I have to go through each fellow to see who has a red hoodie. Right? Everybody got David's question? Right? So the best case is the first fellow I found has a red hoodie. But the worst case, I have to go through each fellow. We'll see what that looks like. Actually, let's use our fellow right here. We have Julia. Okay, great. So for a typical question could be, find me a fellow where the name is Julia. Yes?
So like yesterday, I was doing this pencil and I was looking on how to print like the first 3 elements in an array. So
There's a prefix. Look at prefix.
yeah, I think I would have.
No, but look at prefix. If you're trying to print the first 3 or whatever, you could get.
Those 2 have to run through.
Prefix gets a subscript. So if you look at prefix, I think it's ConstantTime on the Apple's documentation because it indexes like the first 3 elements for you. It's a prefix. Actually, let's look it up real quick. David's question was, he was trying to get the first 3 elements in an array. What is the runtime of it? Apple does a good job sometimes with documenting what the function runtime is. So let's see what that looks like. Let's see if we have a runtime for prefix, right? So prefix on an array, Swift. Prefix here. Let's see. So complexity, normally it's around here. There we go. So I was right on that one. Right. So the complexity of prefix is constant. Because as I assumed, it will take a chunk of the first array. The prefix will always be the beginning of that array. Right? Everybody sees where the complexity is? Everybody. Apple simply says complexity is big O of 1. The complexity of the prefix function. So David was trying to use prefix to get the first 3 elements in an array, and he was wondering about the complexity, correct? Correct?
Yeah.
Right. So the complexity or the runtime of prefix is constant. Do we see that? Cool? Questions? David was asking about the complexity of prefix. Like on an array, I could say prefix, get me something. Get me the first 3, or get me the first 1. Let's go to playgrounds. So on my fellow here, yeah, go ahead.
So today, like, it asks like the first 10, right? But then it only return 5. So it won't give you a compiler if you ask it for 10, but then it only has to be 5.
Let's see what it returns. Let's see what it returns. So let's go ahead and say first 2 for now. First 2 fellows. And fellows, do we have a fellows array? Yes, we do. Fellows dot prefix. And let's get, so prefix returns you an array slice, right? So let's say up to 2, or up to 1, sorry. So use prefix up to. So prefix up to 1. Let's see what we get here. So print first fellows. First 2 fellows. Let's print what that looks like. All right, so here we got Mel. Let's do 2. It's not indexing at 0. Okay, it's not indexing at 0, sorry. So the first 2 fellows, you pass in number 2. It got us Mel and Yulia. Are we able to get that on our playgrounds? And then your question, let's see if we get, my assumption is it will get you the entire 3. Let's see what happens here. So if we say we get the first 10, it actually crashes. It doesn't even return an optional. So that's a bit dangerous. So you want to verify what you're doing before you use an explicit number on that. Ideally, it should return an optional. What's that? Which one? This one? I think they're using not up to. They're using, let's see, prefix, numbers, prefix, 10. I think they're not using up to. Let's see this. Let's see what they're using here. They're not using up to. So remove the up to and just put in the number. Okay, Tiffany? Okay. So here it got us the entire array like we first assumed. So don't use up to, just use the number. Right? So David, again, your answer is it's constant.
I'm still not understanding why it's considered just one.
Because it chunks out. It's a slice. You see what it returns? It returns an array slice. It takes a slice like you have a pizza. Get me the first half. It takes a slice of that pizza. Exactly. So it's also always constant. If I say every time I want to have a pizza, I want to have half of the pizza. No matter how large the pizza is, it's constant. It doesn't change.
I thought it was
Going through each, no. So it doesn't go through it linearly. It just chunks it out. Like it takes a slice. Like if you option click on first 2 fellows. If you option click on first 2 fellows, what type is it? Option click on first 2 fellows. It's an array slice, right? It's a slice of an array, of an existing array. So it just slices of the array, constant. There's also a suffix to it if you want to get the end of it. Cool? All right, great. Thank you for that, sir. So here, this doesn't belong here. Put this in the constant time block here so we don't get confused. So here, that's constant time. You could put some notes here. So here, this is constant time, prefix on an array. Okay. Any questions about constant time? We know what constant time is now, pretty much, right? Yes, sir.
So that one, even though it's technically printing out multiple elements, it's still constant time between either parts?
Yes. Not even iterating, it just chunks out, it takes a slice of the array. It takes the first whatever X amount of elements you have. Okay, good. A next built-in function that's constant time we've been talking about is a set. So if I have a set here, I'm still in the constant time block. If I have a set, I create a set of numbers. I create a set of numbers and I say numbers that contains 2 or 3, whatever. Contains here is very easy to miss contains on an array or confuse contains on an array and contains on a set. Contains on a set is constant time. Why is it constant time? Because the set itself is hashable, and we spoke about hashable elements earlier. Hashable makes it constant because every element is unique. It's unique. I know exactly there's only 1 3 in there, so the operation to get to that 3 is constant time. There's no way I have 2 3s in my set. Everybody with me? As opposed to an array. Right? So that here is constant time as well. Contains on a set is constant time. And as I said, if you hesitating and you're not sure what a data structure runtime is, yes, Amini? Yes, yes, yes. It will return the first 3 it gets, but it still needs to go through the whole array to find out that first 3. Or what you want to find out, does it contain a 3? Not how many 3s. Cool? So it still needs to iterate through the array. And when we talk about runtime, keep in mind, runtime is not the best case scenario. It is not the best case scenario. When we talk about runtime in an interview or anything, they were talking about what's the worst case scenario, not the best case. What is the worst case that I go through an array looking for somebody with a red sweater on? What is the worst case for fellows? I need to go through each fellow. That's the worst case. That's what we're looking for. The best case is, hey, I go through a fellow, the first fellow has a red sweater on. That's not what we're looking for. We're looking for the worst case, okay? In that particular instance, always the worst case scenario. Everybody with me? This is very important to remember. No, because it's not iterating through the set on contains. Contains does not go through 1, 2, 3, 4. No, it uses the hash value of the 3 and just indexes into it. Very good question, very good. It's almost like a dictionary. They almost should change that, like it's kind of confusing, contains. But it's very similar to indexing into an array. But here you have a contains keyword. Next question. Okay. All right. So remember, if you're doing something with contains, a set is better. That's what we did yesterday with our game, our guessing game. We made it a set, so it's on contains, it's constant. And if, as I said, you could always go back to the documentation here, and I could simply look up set Swift. So if we go to set Swift, and we go down on that page. So I'm on the set page for the Swift documentation. Complexity, let me just search complexity. Command F, complexity. Nothing. Contains, sorry. I'm looking for contains. So if we go to this, if we go to set documentation and we look at contains here, and I click on contains, so contains on a set, remember, on a set, the complexity is constant. Do we see my screen? As opposed to an array. If we do the same thing for an array, it would be linear. It would be big O of n. Everybody with me? Go ahead and do it. Like search for array Swift and let me know what the complexity is. On contains. Array Swift, and tell me what the complexity is for the contains function. able to see big O of n, right? So now with conviction, we could say what's the difference between contains on a set and contains on an array, correct? Right? So here we saw two complexities there. Great. All right. Any questions before we move on? Yes?
So for the set, I kind of don't get like, okay, so if I put the array 2, 3, 5, 7, 3, right? So it's automatically going to turn into a set.
Okay, so the inner parts of a set, right? Two needs to be hashable. We likely spoke about hashable, right? So 2 here has a value, a unique value. I can't have an next 2 in there, correct? I cannot.
I mean, you can't, but like if you type it that way, you're gonna like convert that to just having 1, 2. Like say you write let prime set equal open bracket 2, 3, 5, 7, 2 close bracket. Is it automatically gonna just convert to 2, 3, 5, 7?
Yeah. Remember we have an array. If we have an array and it has 3 2s in there, and we convert it to a set, it gets rid of that extra duplicates, right? And then now my 2, 3, 5, 7 is unique. When I say contains x, whatever x is 5, it hashes through its hash table, and it gets me that value. In that case, it just returns true. The value exists. Because the set knows its values, right? So it doesn't have to go through each value because there's no duplicates there. That's the only way it works. Cool? Any questions? Yes?
Wouldn't the array stop when it hits the first?
It will return true. It will stop. But stopping doesn't make it less of a linear algorithm. Because remember, the worst case. Worst case is what? If I have 10 objects, what's the worst case? What's the worst case? Do I go through one object or all the 10 objects? All 10 objects. So it's always n, even if the first object is 1. Cool? Any other questions? I'd rather us understand constant and linear than just going through all of them. So if you have any questions, like please ask. But now we know what constant is. Get me that object. Linear, go through each fellow and find out who has that red hoodie, or find out who took my muffin this morning. Right? That might be harder to find. N is linear. And the bigger one is constant. Perfect. Okay, so we spoke about, this is linear here. I'll grab that header and I will do a next header. And here we'll do log n. Log n is also known as logarithmic. Logarithmic runtime, or logarithmic time, log n. Let's do an example. So here I have a constant. Let's set it to 16. I have a variable j, assign it to 1. And here I'm using a while loop. So I'm saying while j is less than n, go into my while loop and perform an operation. The operation says increment j by 2. Right? Remember when we said log, we said it splits it up. So if I have 16, it splits it up to 8. 8 splits up to 4. Right? So here, this operation is a logarithmic operation. Why is it logarithmic? Every time it goes through that while loop, it increments j by 2. Right? So instead of this happening linearly, going through each element, it jumps each element by 2 on each iteration. First iteration is 2. Right? Then 4, then 8, then 16. Everybody with me? So here it doesn't go through every element. We'll print it out to show you what's happening. The first time I go inside the while loop, what is the value of j? J is 2, right? J is 2. When I go back through my while loop, what is J? 4. When I go back to my while loop, what is J? When I go back to my while loop, what's J? Is 16 less than 16? How many times is this algorithm running? 4. So we said log 16 is. You could simply go to Google. Google is pretty. Let's see. Let's see if Apple could do it actually. Command space. Let's see if we could do log right here. So do log 16. Apple, come on. Can't even do that. It takes us to Safari or whatever. Let's go to Google and do log n. So go to your Google page. Or can I just do it in the browser? Log 16. Log 16 base 2. It doesn't do it. I'll get a calculator for you guys. I'll send out the calculator later. Anyway, if you get a calculator, slack me the calculator, but there's a log out calculator that could do this for us. It's in base 2, right? For now, let's run our playgrounds and see how many times it does execute. So our playgrounds executed 4 times. Do we all see that? Right? So it doesn't execute 16 times. If I was to say while, like our fellows, while fellow in fellows, go ahead and print fellows, we saw it went through each fellow and it printed each fellow, correct? Here we are splitting our while statement. Every time it goes through the while statement, it cuts that problem in half. Anytime you cut a problem in half, this is considered to be logarithmic, right? We'll come back to that later in Unit 3. This is a more advanced topic. As our skill level goes up, we'll go into talking about binary search, right? But for now, I'm just introducing what log n looks like. What does log n look like? For now, just know it splits that problem in half. Every time, it splits the problem in half. Everybody with me? The first time, we got to 2. Next time, we got to 4, right? It's in halves. Next time, we got to 16. The problem is done. It did not take 16 iterations for it to get executed. It took 4 operations for it to get executed. If we were to put in 32 here, what would be the answer? All right. If we were to put in 8 here, what would be the answer? Yes, go ahead.
So when this log is, I think that's how the calculator is talking about. When I put it in, the answer is 4.
Can you slack it to us, please? Yeah. So give Tiffany a hand there. Thank you for giving us a calculator. Where is it? Kristen, you're trying to beat Tiffany to it, huh? Okay. You got it 5 days ago? Man.
My question is, is it going to do the log? I know I have something to do with the exponential, like.
Yeah, there's like a reverse exponential thing, and yeah.
The log base of 2.
Base 2, base 2.
Log base 2 of 16 would be like, how many times would it take 2 to get to 16 that is more?
Given 16 elements,
Right.
how many times will that operation take to complete? In our case, 4 iterations.
Because 2 to the 4th power is 16.
Based on 2, yes. Cool? Very good. So keep that calculator handy. Thank you again, Tiffany. Yes, question? It doesn't come in, 1 second. So the first time it comes in here, it's 2. The second time it comes in, it's 4. Third time it comes in is 8. It comes in at 8. Remember, it comes in at 8. Right? It doesn't come in. When it's 16, it's done already. It does the 16 before it finishes the while loop. The first operation is 2. The second operation
The
is
first time it comes from 2, but it comes 1.
1. Exactly, exactly, exactly.
And the second, but I don't understand when you say the split top. What is that?
Well, in that case, it reverse splits it, it doubles it in that case, right? So it went from 2 to 4. The problem got doubled in that particular case. But in the case of a binary search, it would split the problem in half. So if I'm searching for something, I'll talk about binary search later, right? But if I'm searching for a particular element, I need to break the problem in half each time I go. Here, it doesn't break it in half, but it increments in half, right? It increments in half, 2, 4, 8, 16 on every iteration. Okay. As I said, the one thing I want us to take back from log n is know that the problem on every iteration the problem increments or decrements by half. Yulia, is that better for you? So on every iteration, the problem either increments or decrements by half. In our case, it incremented by half. Cool? Whatever the value was, right? Or double.
So it's always going to be
Increments or decrements by- Yeah, go ahead.
So for the example we said, like, what if you make GAP and it only has to run through the one time or it can be multiplied by itself to equal 2? That would not be a constant time even though it's so fast.
Anything we're doing here right now is not constant time anyway. Right, Tiffany? Right? Because we're iterating through whatever j is, right? So the best case scenario we had here was log n, right? Not constant.
Even though it was very fast.
Doesn't matter. We still had to do double the work on each time in that case, but not every single element. Instead of going to 16 elements, we went through 4 iterations instead of doing 16 iterations. So, for example, if you have like while, 1 second, Christian. So while count is less than 10, for example, print count and have a count of 0. What do we need? Am I done with that while loop? What happens if I execute my playgrounds right now? Very good. So what do I need to do? Thank you. Did we all catch that? Right? Be careful with while loops. While loops doesn't have the fail-safe like a for loop has. For loop, you don't have to say count plus equal to get to some point where you stop. So here we started at 0, and we're incrementing by 1 until we get to 9 here, and it's going to stop, right? So, good. So at this point, what is the runtime of this particular algorithm? Linear, right? Because I have to go through each element here, right? So if we run this playground, it goes through each element, right? As opposed to that while we had up here. This one goes through each element until it gets to that last element, right? So this one is different. This one goes through it logarithmically. So as we saw, log 16 was 4. But here we're going through each element here, and we're printing each element out. Yes, go ahead.
Is it log? Is it log?
Oh, did I spell this wrong?
Yeah. Is it that because it's time?
Logarithmic.
Because it's being multiplied by 2 each time?
But by each time, yes.
That's why.
Yes, because each time it doubles each time. Did I put double here? It doubles. On every iteration, the problem increments or decrements by 2. I'll put by 2 here. Yeah.
So what would happen if it wasn't 0?
The 2 here it doubles its value.
Yeah, I mean, like, you say it's like having or it's incrementing or decrementing by 2 because
Not by 2, by double the value, by double the current value.
So if it wasn't double the value,
Oh, if this particular one wasn't double the value, it would be a different algorithm. Like, yeah, it would be a different algorithm.
I'm also trying to figure out like why this is really taking more time because it's iterating like a similar amount of time, right?
Well, no, one is 4, one is 10.
So isn't that actually like less?
So this one is better. That's what we're saying.
Oh.
Yeah.
Even though that one's constant.
This one is not constant. This one is not constant, Matt. That's not constant. This one is linear. Yeah.
So linear is still faster than
Log n is faster.
Log n is faster than linear.
Yeah. Right? Let's go back to the chart to visualize it. So here we have, at the bottom on the chart, we have constant. Do you see the chart?
Yes.
Then we have log n, right? And then above log n, we have n. Everybody has access to the chart? All right. We'll do one more, and I think we will wrap up for today. I did promise 1 hour. Yeah. Let's see a next example before I answer that question. Okay? Because we cannot assume. Remember, we cannot assume with runtimes.
Yeah.
Okay?
But so far, that's
Yeah, let's not make that assumption. 1 second. Make sure we have that bookmarked, right? So far, we've seen constant, we've seen log n, we've seen n multiple times. N log n, no sorting algorithm is n log n. Okay, everybody? Know the sorting algorithm that Apple has when we say dot sorted on some element, that's n log n. And again, if you want to go ahead, go to the documentation, you'll see the complexity of sorted on an array is n log n. Everybody with me? We'll talk more about and see what that looks like in code in a few units. But for now, no sorted is n log n. If you see it on a question, it's n log n. Okay? Okay, so this is good. Let's do a quadratic runtime, and I think we will. Actually, we could do an n log n. Yes, go ahead. Underneath the linear. What number? What number? Oh, this one? Yeah, move that one, yeah. I was thinking of doing that, but I don't want to distract you guys too much. Thank you. Yeah, I'll move it. Thank you. I'll move that one to, where are we? Here? No. Yeah, sorry. Thank you, Lydia. All right, cool. So we saw, time just flies. We saw constant, we saw log n, we saw n. We could simply see, n log n, an example of it. Grab a header. And let's do n log n, see what that looks like. We could use our same example. So you could copy that example here. You could copy that while statement. I know I'm doing something. Okay, that's good. Not this one. Grab this one. Grab that while statement here. Copy that while statement right below big O log n. And let's make an example of n log n here. Okay. The n and j, yeah. So copy the n and j, don't paste it in yet. We'll say for I in some value, 0 to, for example, 10 or some list number. For now, just do 10. And then paste in our while statement. And let's do some edits. Okay. N is still 16. We could take that out because we know what n is. J is the same. J. All right. We could keep it like that. That's good. We never use I. All right, I'll give you guys a couple minutes to catch up here. So here we're demonstrating what n log n looks like. So we know already the inside was log n, correct? Correct? We showed what that looked like. We said it printed how many times? 4 times, right? So now we have an outside loop which goes through some sequence 10 times, right? We're going through some sequence 10 times here. And let's see what happens here. Anybody knows what the actual time will be? Like how many times will we go through this loop? 40, right? Very good, Chelsea. So how did you come up with 40? Very good. Anybody else? Yulia, how many times do you think this goes through? 40, and then you came up with 40 by? Okay, so you multiply them, right? So when you have inner loops like that, you multiply them. You multiply the outer one. In that case, we have 10 here. So this goes through 10 times. And this here, we said it goes through 4 times, right? So we said 10 times 4, we came up with 40. Let's run and confirm that. Right, so as Julia and Chelsea pointed out, we do go through this algorithm 40 times, right? The outer one goes through n. The outer loop goes through big O of n, right? And the inner loop here goes through big O log n. Right? So that's how we came up with n log n. It goes through n times multiplied by log n times. Okay? And as I said, an example in Swift is dot sorted. Thank you very much. Cool. And later we'll see merge sort is using that same algorithm. Merge sort and quick sort. What's that? You're not getting the runtime we came up with? Make sure you're running your playgrounds at the bottom of your for statement and not in between. So make sure you're executing your playgrounds at the end of your playground. Okay, we'll do one more today, and we'll call it a day for now. We'll do quadratic or n squared. So grab a title, and let's go ahead and do quadratic n squared, also known as quadratic here. Okay, let's create a list, an array of numbers, 1 to 10. Awesome. So here we have a list of numbers 1 to 10. We'll use a for loop to iterate through it. So here we're iterating through the for loop once, right? So we're going for I in 0 to list.count, right? And inside that for loop, we have a next for loop using a different variable. So here we have for j in 0 to list.count. And here we are printing list I times list j equal to list I times list j. Cool. Great. Anybody want to walk me through the runtime here? Anybody want to walk me through the runtime and why it's n squared? Adan? Yeah. You could walk us through it, what you're thinking about. That's part of the process of the whiteboarding, right? You think out loud. So what's the first for loop doing? He's iterating through the list, right? What's the second for loop doing? The same thing. That's same thing. That's what I'm looking for. It's going through the same thing. So what would you say the first line is doing? That first for loop. What runtime would you say it is? Big O of what? Many are dancing here, but I'll take it. Okay, so N. And what is the second one? So the first going through the same collection. Line 85 is going through the list. So far, so good. Line 86 is going through the same list. So if we use n to represent the elements here, it's going through the same elements twice. So as we did earlier with n log n, we multiply our algorithms here. So it becomes n times n. What's the n times n? N squared, right? So here that algorithm is n squared, or known as quadratic. So that here is quadratic. If I have 10 elements, how many times will this particular algorithm get executed? 100, right? Matrix, correct? Right? So it gets executed 100 times. Why does it get executed 100 times? This happens how many times? 10 times. And what did we say we're doing? We're multiplying it, correct? So we multiply 10 by 10, and we do get 100. Right? Let's run it and see what's happening here. Look at that, right? So we on point. It's 100 times. So you see how my input, as my input grows, the amount of work I have to go there, I have to do here, grows as well. If I have 1,000,000 objects, I'm going through the 1,000,000 times 1,000,000. At this point, your algorithm just gets really, really slow. Everybody with me? So when you catch yourself doing some for loop with a for loop, think about how can I optimize this, right? As a matter of fact, if you do have stacked for loops, let's show one example, and then we'll end it here. Right? Let me get an example here so we don't get too confused. Actually, that's a good one. I will slug that one out to you guys, and let's see what you come up with. Okay, I slacked out a code snippet, paste it into your playgrounds, and get a new headline. and call it deriving compound runtime. Runtimes. Right? Anybody want to help me figure out what the runtime is here?
You set it up.
Yeah, I stacked it out. I call it deriving compound runtimes. Compound meaning they're stacked. We have loops stacked on top of each other. In this case, it's not, well, we have nested for loops as well, but we also have for loops nested on top of each other. So it's compounded. Yes. And again, remember, we're looking for the worst runtime, the worst case scenario. So Chelsea was saying, so Chelsea is saying it's quadratic. Why is it quadratic?
I mean, that's the highest that I understand, and the lowest, like the bottom part of the code was like at the very least, and that's what I understand.
So yes, so you're looking at the entire function. Everybody, we're looking at the entire function as a whole, right? We go through each runtime here. We look for the worst case scenario. The worst case scenario is I get here, I go through my first for loop. What's the runtime of this particular for loop on 103? What's the runtime of 103? Okay, so this is big O of n. And what's happening on 104? I'm going through the same array, right? So this is also big O of n. And we know in that case we multiply it, so it becomes n squared. So that compound runtime here is n squared. Everybody? Yes?
How do we factor in the if-else?
The if-else statement, you could walk through it, like what's happening here. That's a constant time, right? Whatever is happening there will happen regardless of what size of array it is, right? Index is a constant, so index 1 is not equal to index 2. That's basically comparing two variables. That's a constant time equation, right? Is 2 less than or equal to 3?
So when we're taking into
Consideration, you go in only if it's the same collection. If it's not the same collection, everybody please pay attention here. If in case I'm going through some array 2 here, like just call this array 2, I know I'll get a compiler error. But if I have array 2 here, right, that is not no longer n squared. Everybody with me? This is a different collection. You still multiply it, but it's no longer n squared. You could say n times m, as in Mary, okay? So that becomes n, and then here you could call it m, for example, okay? So it's not n squared, it's n times m. Different collections. Collection 1 is array, just array. Luba? Collection 1 is just an array. Collection 2 is a different array. Okay? So it becomes n times m. Yes, sir?
If you wanted to find the total runtime of the function,
That is the total runtime of the function.
it's just
It's n squared.
n squared.
You look for the worst case scenario. You don't look for the best case scenario. You look for the worst case scenario. Worst case scenario, I come into this for loop twice on the same collection.
So if there was like 3 quadratic things, would we still only refer to them as quadratic?
You have an next for loop, you mean?
Like let's say there was enough of quadratic like for loop separate from
Oh, you mean like a stack one? It will still be n squared.
Okay.
Right? So if I was to copy this and paste it at the bottom, you mean?
Yeah.
Yeah, it would be the same.
It would be the same.
Yeah. On the lesson, we have more exercises. If you go back to the lesson, again, this will live with you throughout your careers. As long as you live in job 1, you go to job 2. Unless you're a senior, even a senior, sometimes you'll still get asked, you'll probably get asked more system questions, like design questions. But knowing big O is relevant for the rest of your career. So on our lesson, we have more examples here of compound runtimes. Let's look at the last one. Do we see the very bottom? Can we see the very bottom here? On the lesson, example 5? Do we see example 5? Can we see example 5? That's the last thing for the day. Example 5 says second smallest, right? Before we click on the solution, we all have access to the lesson, correct? Before we click on the solution, anybody want to walk me through what the runtime is here and why? Luba, what's the runtime of the first statement? That guard here, what's happening here? What runtime would you say is happening here? Guard my array that count is more than one, else return. It's n, because if you look at count, count itself is n, right? That count goes through each element. Okay, let's keep going. What is the runtime of my array square bracket 0? Constant, very good. This here is a constant. We're not going to keep that in mind here. What happens here on that follow? What is the algorithm of this guy? Next person, Mel, what is the algorithm of this statement? For index num in my array, whatever I highlighted, what is the runtime of the highlight portion? What's that? You said n, right? Because it goes through the array, whatever elements it has, it goes through that entire array. So that's n, right? N elements in my array goes through that array n times. So far, so good. What happens on line where it says second min here? 1, what happens on second min? What's the runtime of second min? So my array index 0, what is that? Constant, right? Min here is a constant. That variable is a constant. So that entire line is a constant, right? We go back to this for loop. What is the runtime of that for loop? Next person, Cassandra. What is the runtime of that particular for loop? No, we're not dividing anything here. We're actually going through the entire thing. So that's n, right? The print statement just returns something, or it just prints what the thing is here. So as we look at that entire algorithm, what is the final runtime of it? What's the worst case runtime we came across? O(n), right? So that entire function here is O of n. Everybody? Right? Again, you look through every individual line, see what each loop is doing. You see what I did, right? So you go through this for loop, you put a comment to yourself, this is n. You go down, this is n. If you see an n squared, you put the n squared. If you come across an n squared in that particular algorithm, the worst case would be n squared. Everybody with me? It was linear, yes. Right?
Okay, so when we find like 3 ends, we can find
As long as it's not embedded. If it's not embedded, right? Like if I have a for loop inside of a for loop, then you have to say, am I multiplying n times n? Is it n times m? But if it's stacked one on top of the other, then you add them. You add them and you get rid of the constant. So if we have to add, guys, 1 second before we stop. So here, if you add n plus n, what is that? N plus n is what? 2n. In big O notation, we do not consider the constant. The constant is a 2. So we don't count the 2. We get rid of the 2. If there's a 2n, we get rid of the 2. It becomes n. So this algorithm is simply n. Okay? It's linear. Worst case is linear. Okay? Again, we'll revisit this. We might even do a pair programming thing with that same lecture here, that same lesson. But today we're just introducing us to what big O notation is. So now when I ask you what's the runtime of contains on set, you know what the answer is? Right one, what's the runtime on contains on a set? Constant, right? And what's the runtime on contains on an array, Tiffany? Linear. Very good. So that's the objective of the data. I will stop. Thank you so much.